All right, in this video, we're gonna see we're gonna continue to look at the section 3.2. Okay, so data approximation and Neville's method. So last video, I introduced the notation that is interpolating some of Lagrange polynomial that agree with the exact function f of x at some of nodes, not all of nodes. And then using that notation, we express Lagrange polynomial and that agree with exact function f of x at every node. Um, the every node recursively. Okay, so what that means, so it's 3.2. Data approximation and Neville's method. So as I mentioned that the objective of this section is to construct the Lagrange polynomial, the formula of the Lagrange polynomial recursively. Okay, so we can so we want to design the algorithm, the Lagrange polynomial with a low computation cost. Okay, so the first one, PM, less than what we saw, is a PM, M1 and M2 through the MK, okay, of x. This is a Lagrange polynomial that agree with f of x at the k points, okay, out of the n plus 1 nodes. So k nodes out of n plus 1 nodes, okay? So this is the Lagrange polynomial. That agrees with f of x at x sub m1, okay? So x through the x sub mk. So m sub 1 through m sub k are indicate nodes, indices of nodes, okay? So for example, x sub 1 could be x sub 2 through the and then x sub m2 could be x sub 5, something like that. Okay, so example was this, let's say x sub 0 is 1.5 and then x sub 1 is the 2.1, okay, and then x sub 2 is 3.2, and the x sub 3 is the 3.8. Okay, all right. Then P1, then P what 1, 3, okay, of x. So 1, 3 means 1 and 3 don't do not mean the first node, third node. The x, I mean the 1 sub index 1 means actually sub x sub 1, and the 3 means x sub 3. Okay, so this is going to be x minus x3. What that means, this is going to be what? Actually L, right? You can say, yeah, I'm sorry. We cannot use the notation L, right? Sorry. So x minus the x3, which is 3.8 over, okay, and the x1, which is 2.1 minus 3.8 times f of x1, which is f of 2.1, right? So this is 2.1, right? Plus the x minus x sub 1, which is 2.1 over 3. Yeah, 3.8 minus 2.1 times f of x sub 3, which is 3.8. Okay. So now, and then using that notation, we're going to express, that was theorem 3.5. Using that notation, we express Lagrange polynomial that agree with f of x at every single node. That was x minus xj, okay, the p0 through the j minus 1, and then j plus 1 through the k of x minus x minus xi, okay, and then p0 through the I minus 1, the I plus 1 through the k, the x, and then divide by xi minus xj. Okay, so that p of x describes the kth Lagrange polynomial. Okay, kth Lagrange polynomial. Okay, so now the next one. So we proved that this the p of x, that expression, and this is the this formula is nothing but the this formula to satisfy the Lagrange polynomial property. It means that the p of x agree with f of x at every single node. We proved that. Okay, now we're gonna and then we introduced I introduced Nevilla's method. Okay, so in Nevilla's method, okay. So I told you the objective of this section is to construct interpolating Lagrange interpolating polynomial can be generated recursively, right? So that's the what the that algorithm is called the Nevilla's method. Okay, so we're gonna introduce a new notation qi comma j. Okay, so the qi comma j is nothing but pi minus j through the I minus j plus 1. Oh, not through the, I'm sorry. So I minus j and then I minus j plus 1 through the I. Okay, so that's quite the long expression. So to express this one in shorten, we use this one qi comma j. Okay, so here I subindex I indicate n number. N number means the you see that here last subindex of p that indicate what the index of nodes. Okay, so now the j that represent the degree. Okay, right. So how many then how many nodes this Lagrange polynomial agree with f of x? I minus I minus j plus 1, right? Okay, so this is there are this guy agree with f of x at I minus j plus 1, which is what? Which is j plus 1, right? j plus 1 nodes. Okay, since this guy, that Lagrange interpolating polynomial agree with f of x at j plus 1 nodes, so the degree of p must be j. That's why you see that. So the second subindex j means degree. So now the key in mind is here for the j must be between 0 and I. Okay, so that makes sense. The degree must be what? If j is greater than I, it means the degree is greater than what? You see, if it is j, I mean j is greater than I, then we're gonna get the give me a second. Let's see, minus 2. Yeah, so j cannot be I'm sorry, j cannot be the greater than I, right? Because the degree must be less. Degree must be 1 less than the number of nodes. Let me see. Okay, so now and then the last time, so we expressed the what? We expressed the Lagrange polynomial agree with the f of x at the 1 nodes, 2 nodes, and 3 nodes using that notation, right? What that means, first we assume that x0, the x0 and then x1 and x2 through the maybe xn right there. So for given nodes, and then with the given the function value for each node, f of x0, f of x1, f of x2 through the f of xn, right? So these are nothing but what? P0, P1, P2 through the Pn, right? We can say that. Okay. Why? Because P0, see that here, notation of P is this. You see P1, 3. P sub M1 through the Mk is what? Lagrange polynomial that agree with f of x at these nodes. So P0 means that what? Lagrange polynomial agree with f of x at one node, at one node x0. It makes sense, right? So now we can express the P0 through Pn using the notation Q, which is this is Q 0, 1, right? 0, 0, and this is Q 1, 0. Is it? Q 2, 0. Q this is gonna be n, 0, right? Right. So now I'm gonna construct the Lagrange polynomial that agree with f of x at x, see that x0 and x1. Okay, but this one to construct this one, I'm gonna use the what? That formula in theorem 3.5. Okay, so now then we're gonna get the q. This is equal to q 1, 1, right? Why? Because degree of this guy is 1, and the end number, I mean end index of the node is 1, right? Okay, 1 right there. This is end number or end index of the node. Okay, and then since this guy what interpolate the x0 and x1, so degree of p must be the degree of this guy must be 1. So that's why the second index of q is 1. Then using theorem 3.5, okay, this is going to be x minus x0 and then q 1, 0 minus x minus x1 and then q 0, 0. Okay, divide by and then x1 minus x0. Okay, so how can you get this one from 3.5? So I explain how can you apply this one to get that expression in the last video. So please look at watch that the previous the last video, then you can understand that. So now then So what? So just keep the constructing Lagrange polynomial, interpolating 0, 1 and 1, 2, 2, 3 through the n minus 1 and n. Okay, and then using these Lagrange polynomial, we're going to construct the what? P0, 1, 2, P1, 2, 3 through the Pn minus 2, n minus 1, n. Okay, for example, P1, 2, P0, 1, 2, that is equal to Q, what, 2, 2, right? This is equal to Q3, 2 through the what? This is equal to Q, what, n, 2, right? So that is equal to x minus x0, Q2, 1, and then minus x minus x2 times Q1, 1 divided by x2 minus x0. And this is equal to x minus x1 q 3, 1, right? 3, 1 minus x3 x3, yeah, and then q 2, 1. Okay, why? Q3, 1, what does that mean? Q3, 1, I mean divide by and then x3 minus x1. The Q3, 1, what does that mean? Q3, 1 is equal to, I told you, the second subindex means the degree, and then 3 is the n number, right? Isn't it? So this is equal to P what? 1, 3, right? Okay, so degree 1 means that what? This guy interpolate the two nodes, right? Okay, and the 3 is a last index 3. Okay, then okay, well, so P1, 3 is it 1, or we can say this is equal to P I minus j, and then I minus j plus 1 through the I. Okay, so what is I here? I is Q3, 1, I is 3, right? And then j is 1. Okay, isn't it? So this is gonna be what? J is j equals 1, I is 3, so we're gonna get P 3 minus 1, P2, comma I minus j plus 1. I mean up to I is what? 3, right? So B, this is 3. Yeah, P2, 3. I'm sorry. Yeah, it's not 1, 3. So what about the Q2, 3? Then Q2, 3 is can you look at this? Yeah, so Q2, 3 is what? So 1 is the degree of the polynomial, right? And then 2 is n number. So this is equal to P, and then I mean 2 is I, right? And then 1 is j, right? So I minus j, which is 1, okay? And the n number 2, P1, 2, okay? So then that makes sense. Why? Because look at the theorem 3.5 in the formula in 3.5 here. So P of x, this one can be expressed as like this: x minus xj times P. See that? The Lagrange polynomial. Look at the sub indices 0 through the k except for j, right? And then minus x minus xi, and then see the p with the sub indices from 0 to k except for I. So now then here x minus x1 times that Lagrange polynomial must be what must interpolate f of x at what nodes x I say the x x all nodes except for x1. This makes sense. Okay, so now it makes sense. We see p2, 3 right there. So p2, 3 is what? This is long interpolating polynomial a group with f of x at x2 and x3, not x1. Okay, so this is what long interpolating polynomial. I mean that one interpolate f of x at x1 and x2, not x3. Does it make sense, right? Okay, so now so this one, the now we see that. Okay, now give me a second. Yeah, so we just keep going, right? Q here. So finally, to construct, for example, p, keep doing that, then p0, 1, 2, 3. To construct this one, we need the two previous information, p0, 1, 2, and then p1, 2, 3. But these two Lagrange polynomial, to construct them, we need those information. 2, okay, and then p2, 3. Okay, so it's see that we can then now we see that we can figure out the Lagrange polynomial recursively. Okay, so to construct this one, well, we can use these information we already got. Okay, well, by the way, this is equal to q. What? How many nodes? This guy interpolate 1, 2, 3, 4. So degree must be 3. Okay, and then the let's see, what's the n number? 3. So this is 3. q3, 3. This is equal to x minus x0. Okay, and then q. What? This guy told you. This guy what? Must interpolate nodes x1, x all nodes except for x0, right? So this must be q 3, 2 minus x3, right? Okay, so this is j, this is I. We consider that in theorem 3.5. Okay, so and then q, and this Lagrange polynomial must interpolate all of nodes except for 3. Okay, so that must be q 2, 2, right? Divided by x3, x3 minus x0, yes. Okay, so now then how can you design the algorithm generating this one? Okay, you see? Okay, so we'll see. So now, so first one, this is algorithm 3.1. Okay, so Neville's iterative interpolation. Okay, so now in this algorithm, the output is the excuse me. So the goal of this algorithm is to evaluate the interpolating polynomial p of x, okay, on the n plus 1 distinct nodes, okay, on the x1 through the xn plus 1. Okay, I know that we have used the sub-indexes starting from 0, right? x0 through xn, but we're gonna since we use the MATLAB, so MATLAB, the sub-index in MATLAB should start from the 1, so I changed the sub-index starting from 1, not 0. Now, this one on here for the function f of x. Okay, suppose we assume that we don't know this. So now input must be what? Nodes, and then function value at each node, right? So x1, let's say just x input. First of all, we want to evaluate p of x, right? So we need, so the x value must be input, okay? And then nodes, okay? Nodes x1 through the xn plus 1, okay? Now the input. Second one is values, f of x1 through the f of xn plus 1, okay? So actually, what? This is equal to q, 1, 1 through this is the q n plus 1, 1, right? Okay. Now then, output is the matrix q, okay? And the number of row is n plus 1, and the number of column is n plus 1, okay? So each entry means each entry represent the Lagrange interpolating polynomial, okay? And then q, the last row and last column entry, that's gonna be, last row, last entry gonna be the Lagrange interpolating polynomial that agree with the f of x at every single node, x1 through xn plus 1. This is equal to q n plus 1, n plus 1 of x. Okay, so keep in mind that this is actually, this is the number rows, okay? This one means number of columns. Okay, so what we're going to do, so what that means, q. So we need to figure out the structure of the matrix q. Okay, so the first column going to be q 1, 1, q and 2, 1 through the q n plus 1, 1. But these are nothing but what? The function value, the function values of each node given as input, right? Okay, and then using the this is the first column, right? Using the first and second entry in the first column, we can construct what q, what's this? Q1, 1. Q I'm sorry, Q, this is the Q1, 0, right? I'm sorry, Q1, 0, 2, 0, I'm sorry, 0. Okay. So using the first and second entry, first column, we can construct the Q1, 1. And then using the second and third entry in the first column, we can construct the Q 2, 1, right? Okay. So up to the Q 1, 2, 3, and then actually give me a second. So this one, oh yeah, sorry, this should be 2, right? Because Q2, 1, the first subindex means the end number, right? And the subindex of n last node. So it's 2, right? Okay. So it's 2, and then 3, and then through the n plus 1, 1. Okay. All right. So now ending, and then the third column, using those two information, we can figure out what q. We can construct the q 3, 2, is it? So O2 Qm plus 1 comma 2. So you see that here? Now, actually, these are what? Through the final, we're going to get the Q, the N, comma, N. Oh, 1, comma, I'm sorry, Q, N, comma, give me a second. Q, yes. And then Q, N, comma, N, and then Q, N plus 1, comma, N. They're using these two. This is the what? N plus what? Give me a second. Okay, so this is the first column. That's going to be second column, right? Okay, and that's going to be third column. Okay, so give me a second. 1 and okay, and then n minus 1. I'm sorry, this should be n minus 1. That's going to be n minus, oops, n minus first column. Okay. Now then, using these two polynomial, we can construct a q n plus 1 comma n plus 1. Okay, so that's going to be nth column. Okay, and then these are diagonal entry. You see that? These are diagonal entry, and all of entry above the diagonal entry is 0. Okay, so we want to construct the lower triangle matrix whose diagonal entry is these, and the last entry in the last row, in the last column, last entry, that's going to be P of X. Okay, so we're not going to calculate each column independently. No. Okay, so we're going to construct the we're going to calculate the second column, third column through up to through the nth column recursively. Okay, so that we can save save the computational cost. Okay, so now let's see. Okay, now then step 1 is here. Step 1. So keep in mind this. So the what? Give me a second. Q. So first column is given, right? Okay, first column is given. So we're gonna step 1, not this one. Step 1. Before doing step 1, sorry. So first we're gonna enter the what? The input f of x1 through f of xm plus 1 into the first column. Okay. So now we can say Q, the all of row in the first column is equal to input. Okay. So f of x1 through the f of xm plus 1. Okay. That's step, this is kind of step 1. Okay. Step 1. And then step 2. Now when then we using a for loop, we're going to calculate the all of columns. Okay. Before doing that, yeah, I know we need to initialize the size of matrix Q. Okay. So now I'll do this when I write code. Okay. So for I is equal to 2 to n plus 1, right? Because I is the index of row. Okay. Okay. And so you see give me a second. So I is the index of row, okay, and then J is equal is the index of column moving from 2 to I. Okay, so the J, that's the index of column. Okay, so actually I means the what? The degree of degree plus 1. Okay, and then J means the nodes. Okay, yeah, I know. Probably some of you don't get it what that means. So here, what I want to do this is what I want to do is this. So I is what? Let's see. I can see. I is moving from 2 to n plus 1. The I is index of row, right? So for I equals 2. Okay, for example, I equals 2. I equals 2 means the second row, right? This one second row. Okay. While I is 2, the index of row is fixed at 2. The column J is the index of column, right? So J moves from 2 to I, but I is 2. So J gonna move from 2 to 2. So which is what? This one. Okay. So we're gonna calculate when I equals 2, and then when I equals 2, we're gonna calculate the second row and then second column. Okay. And then when I equals 3, the J gonna move from 2 to 3. It means that when I equals 3 means the third row, we're gonna calculate second column and third column. And then I equals 4, we're gonna calculate the second column, third column, and fourth column. When I equals 5, when I equals 1, 2, 3, when I equals 5, we're gonna calculate second column, third column, fourth column, and fifth column. That makes sense, right? Okay. So for each fixed row, we're gonna calculate the entry starting from second column to the ith column. Okay, so that's a strategy. So I'm using 2. Now we calculate q I comma j is equal to x minus. Okay, so the right there. Oops, give me a second. X minus what is you see that here? I told you so. For example, here q3 comma 3. How do we determine I and j? I mean, excuse me. How do we determine I and j in theorem 3.5? This is j, here's I, right? So the first index in P, that's j. The last index must be I. Is it? Okay. So now then this gonna be the what? That should be, I mean, something, and then q I comma j minus 1 minus x minus xi. Okay, so this is gonna be what? X I minus j plus 1. Okay, because the look at this here. When we see a q I comma j is equal to p I minus j, p sub I minus j through the I, right? So I minus j, that's gonna be index j in theorem 3.5, right? Okay, so now that's why I'm gonna subtract the the j from I. Okay, but keep in mind this here in the pseudocode in this algorithm, we start from the sub-index not 0 but 1. Okay, so we're adding 1. Okay, for example, if I and j have the same number, for example 2 or 3, I mean 2 comma 2, 3 comma 3, when you do this I minus j, they won't get 0. There's going to be big you know, we shouldn't get the 0, okay, in MATLAB, so we add 1. Okay, And also we see that we start from the subindex I in the node. Okay, so now then then qi comma why does it qi comma j minus 1? Because right there, I mean, look at the pattern when you figure out the polynomial recursively. So for example, right there, so q3 comma 3 and the q3 comma 2. So second index, sub-index is 1 less than 3, right? Okay. So for example, the other one is the q3 comma 2. This one is what? This the second sub-index is 1 less than this one. So this should be the second sub-index must be 1 less than this, the second sub-index of q, right? And then x minus xi times qi minus 1 comma j minus 1. Okay, and then xi minus j plus 1. Okay, so it's end. Okay, all right, so it's done. Okay, so step 3, maybe you can say it's output q. Okay, but it's end. All right, so I'm gonna write the code. Okay, so but this one, give me a second. Okay, so see, so we need to open a new the M file, right? So I just click this one. So I'll name it. I change the name. Name is method. Okay. All right. Okay. So second, I'm gonna copy this. Okay, this is the Leibniz method, right? Leibniz method. It is this one. All right. So output must be Q, right? Q. Okay. Keep in mind this. The function name must be same as the file and file name. Okay. And the input, by the way, so here input is what? Okay, x and nose. Okay, so x sub 1. But here, the let's say nose. Let's say nose. What x? Let me use Give me a second. Oh yeah, I'm sorry. We don't need Give me a second. Yeah, nose. No. Let me use d. Okay, d nose d. D means the x sub 1, x sub 2, okay, through the x sub n plus 1, okay, n plus 1. And the output, and then the other one, I mean, input nose, and then function value, right? Let me say y, okay, y. Y that means f of x sub 1, f of x sub 2, through the f of x sub n plus 1. Okay, this input, and the output is what? The matrix Q. Okay, matrix Q. So n plus 1, comma n plus 1, this size. Okay. Okay, such that what Q, I mean matrix Q of n plus 1, comma n plus 1, that is equal to P of X. Okay, So now input is x, comma, and then the d, okay, x comma d, right? And then y. But yeah, so to yeah, so well, yeah, there are several ways to write the code, but yeah, x comma t comma y, that's fine. Okay, t comma y, yeah. Or you can combine the two input d and y, okay, as the that what n plus 1/2 matrices, okay. So or you can separate the like this d and y, or you can combine d and y as one input. Okay. So anyway, so so this one, and then first we initialize the q, right? So q, initialize q. Okay, q is equal to what? Zeros. Because you see that I told you here, well, in a matrix q must be a lower triangular matrix, and then upper triangular. I mean the all the entry above the diagonal must be 0, right? So all the gonna fill with the 0 in the Q. Okay, zeros. And the M, by the way, we need to define N, right? Because N is what? N is equal to the length of nodes D, right? Or you can say Y, but doesn't matter. Okay, all right. And then it's gonna be, but actually, what? It should be M, right? M. Let me use M. So what does that mean? Here, M is equal to M plus 1. Okay. So this is M, comma M. Okay. I mean, you can say N, but if you say N, but you might be confused with N and this N plus 1. Okay. All right. So okay. So here, what does that mean? N. N is actually degree of M equals N plus 1, and then N is the degree of P of X. Okay. All right. So now so Q N comma N, and then we do step 1. Okay. So uh, put the y into the first column of Q, matrix Q. So Q of all of row in the first column is equal to what? Y. Okay, but here key man is let's say that we I mean the structure of D and Y must be column matrix, column vector. Okay, D prime. Okay, and the Y prime is prime here. So D and Y must be column matrix. Okay. Now then we do step 2, which is the what? We're gonna construct the we're gonna calculate the entry in the matrix Q. Okay. So let's see, 4. I mean now compute entry of Q. Okay. So for I, give me a second. Give me a second. Here. Oh, yep. For I is equal to true to n plus 1, right? Which is m. Right? M. And the for j is equal to true I. Q I comma j is equal to x minus, okay, x minus d I minus j plus 1, you see? Okay, and then times q I, okay, comma j minus 1, okay, all right, minus, and then x minus x d of I, right, times q I minus 1, comma j minus 1, okay? So, okay, it seems that right? But here's the problem. What if x, your input x is a vector? What if x is a vector? Okay. So, then we're gonna get big problem. But you may just change this one, that operator to dot operator, okay? Or this is dot multiplication, right? But yeah, then we're gonna get big trouble because q I comma j is what? Must be this must be just one single real number, right? But the right hand side is if x is not single number but vector, we're gonna get the vector. So dimension is different, left hand side, right hand side. So we're gonna get big problem. So we assume that here the x must be one single real number. Okay. Now in the d of I, d of I minus d of I minus j plus 1. Okay, I minus j plus 1. Okay. So now then, and all right. Okay. So now q and give me a second. Yeah, I missed the function, right? I'm sorry. And then end. Okay, we save, and then we let me test. Let me test this the code with the example in textbook. So give me a second. Let's see. Okay, I found it. So, second. All right. So, yeah. So let me test this that code with example 2 in textbook. Okay. So example 2 textbook says that example 2, the x0, I mean x0 through x4, which means the x1 through x5, right? It's given. Okay. In this case, we use the letter d, right? D is equal to 1.0, 1.3, 1.6, 1.9, and 2.2. Okay. And then dy is f of 1.0, right? Which is q1, 0, which is the give me a second. That's gonna be, give me a second. Data is given, which is 0.7651977. Okay, and then 0.6200860, and then 0.455, and then 4022, and then 0.2818186, and then 0.1103623. Okay. All right, and then we're gonna calculate the we're gonna approximate f of 1.5. That's a question. Okay, we're gonna approximate f of 1.5. Okay. So now back to the code right there. So we d is equal to 1.0, and then 1.3, 1.6, 1.9, and then 2.2. Okay, and then y is equal to 0.7651977, and then 0.6200860, and then 0.4554022, and then 0.2818186, and then 0.1103623. Okay. D y. Okay. Now we enter those to input into the function Neville. Okay. X is 1.5, right? And then D and Y. Now we got this, that matrix. What does that mean? The first column is nothing but what? Q, Y, right? Input Y. Okay, and then second column represent Q, what's Q 2,1. I mean, from the 2,2 entry, this is the what? Q 2,1. This is Q 3,1, Q 4,1, the Q 5,1. Okay, let's see. Oh, 2, we got this Q n plus 1. I mean, this is Q 5,5, right? Okay. Let's see there. Okay. So now 0.51182. So let me compare this one with the let me see, in the solution example. Yeah. And then you can see. Give me a second. A second. I got this one. How can I show stuff? All right. Yeah. Yeah, you can see that here, table 3.6. That's the table. I mean, this is the. Excuse me. So the example. That's the result of the example. Okay. So you can compare that table with the your result. Okay, but give me a second. Yeah, I think I got the same result, same the numbers as the that table. Okay. So let me stop here. Okay, and then next time I'll cover the 3.3. Okay, so